So the next assumption, the fourth assumption, is spherical disturbances What does that mean? So it means that the variance at time t is 1, or I think we had denoted it as epsilon, right? So let's keep it consistent here. So the variance at time t is 1 is the same as the variance of our error at time t is 2, and it's the same as the variance of our residual of our error epsilon at time capital T. Yeah, so the variance is always the same across time given asset I. Okay, I drop now the index indicating the corresponding asset. Okay, we are now in the time dimension. Of course, the residual, so the variance can vary across assets, but given asset I, the variance should be the same across time. So the variance should be then the variance of epsilon t, given asset I, should be then sigma. And obviously here's no time index. So which means it's the same sigma squared, the same variance across time given that asset. Moreover, the covariance, so that's the first issue concerning assumption number 4. And now it's this, on the second issue, is that the covariance between the error, let's call it k, epsilon k and epsilon l, which denotes now two different times. Okay, k can be, I don't know, if k can be 1, l can be 2, or the covariance can be also between 1 and the first and the third observation, or whatever. So the covariance between the residual k and residual l should be 0 for all k unequal l. So whatever you plug in here, if k is equal with l, it's this guy here, this expression becomes the variance, and the variance we have already defined here. Of course, it's obvious. So, but whenever k is unequal to l, it's not the variance. Then we talk about the covariance. But the covariance should be 0 for all, between all. So there should be no correlation in the time dimension. So I will give you now some examples. So that's our second issue. So I will give you now, we are talking now about some examples. So let's plot here the time dimension t, and here we have our epsilon depending on time t. So what's going on, and I will plot you now a residual process here. So let's say we have this process here. This is how a residual process could look like. So what's going on here? So what we see here is that once we are, let's say, or let's maybe go here. Once we are here at this point in time and the residual is positive, yeah, in the next time period the residual is positive as well. Next time period the residual is still positive. So what we have here is a positive autocorrelation. Yeah? So positive autocorrelation means that the covariance is positive. Okay? So if this is the case, if the residual of your regression look like this, then obviously this assumption here is violated. Okay? So we don't want to have that. Yeah? So OLS requires that our residuals are uncorrelated. So how should the residual process then look like? Again, so next, let's say we have this residual process. What's going on here? So obviously, in contrast to the earlier picture, we don't have this circulating around. Yeah, we don't have positive autocorrelation here, obviously. So, but what do we see here? What we see here is that we have periods where the volatility is very low, is very high, and we have periods where the residual term has a very low uncertainty, yeah? Very low volatility. High volatility, then again we have a high volatility and a period of low volatility. So periods of low and high volatility are alternating. So what happens here is we see that the variance, yeah, of the residuals are depending on where we are in the timeline. So they are depending on the time. Because sometimes it clusters, so we have a cluster of low volatility, high volatility, low volatility, high, and low and high, and so on. So in this case here, the first assumption is violated because the variance, the volatility of our residuals is not the same. Yeah, it's depending on time t. Yeah, but our OLS regression framework requires that we have the same variance. So how should it then look like? How should our residual term look like? That's again plot here the time dimension. So it should look like something like this. It's a completely erratic white noise, unpredictable process, randomly distributed, identically distributed, completely, there's no information given. Yeah? There's no autocorrelation and the variance seems to be the same. This is basically how the residual process should look like. There should be no information in these residuals. Yeah? So that's basically what these two assumptions require. So let's take this away. The next assumption is normally distributed residuals. Yeah? So basically our epsilon t is distributed as, so this means distributed as normal with zero mean and variance sigma squared. If we have it now, and if we take it in matrix notation, this is a vector and this is distributed as normal with a vector of zeros. A t/1 vector, multivariate normally distributed with the t/1 vector of zeros. So the dimension of this vector is t/1, and the covariance matrix with sigma square on the main diagonal. And everywhere else are zeros. So this dimension of this covariance matrix covariance matrix is t by t. Yeah. So that's how we have it, how it would look like in matrix notation. Yeah. And this guy here can be of course simplified because we have only on the main diagonal, yeah, the variances of our residuals. And we can basically write this matrix as sigma square times the identity matrix, where we have on the main diagonal ones and everywhere else zeros. Yeah. So this guy is then basically sigma square times the identity matrix of dimension t. And because the identity matrix is symmetric, it doesn't, if we write capital IT, we know that the dimension is t by t. Okay. So these are different expressions for the same thing. Yeah. So multivariate normally distributed with a zero, with a t/1 vector of zeros as defining the mean, and this matrix here as the covariance matrix of the residuals of the residual term. Yeah, and the covariance matrix of the residual term has the sigma square on the main diagonal, which is the same variance for all of our t observations, and because the covariance between these errors is zero according to our assumptions, below and above the main diagonal are zeros. Yeah? The dimension is t by t. We can write it like this. We can extract, we can put the sigma squared out of the parentheses. What remains is in the ones on the main diagonal. Yeah? And because this guy here is an identity matrix, a very simple identity matrix, we can write it as capital I t of dimension t, and then we know it's t by t because the identity matrix is symmetric. So we can rewrite it then. Basically we can say, okay, epsilon follows a normally distribution with a vector of zeros, dimension t, t by 1, and sigma square times the identity matrix dimension t. Yeah, so that's another way how you could write it. Yeah. So normal distribution as fifth assumption. So what we'll see later on, this the assumption of normal distribution is not the most important thing in showing some statistical properties of our least squares estimator. So let's take this away. So now we have defined our framework, yeah, for what's going on, we have defined our matrices, and what is next is we will now, based upon our assumptions, we will derive the OLS estimator, yeah? Because we will use it in our course basically over and over again. So we need to know what's going on, and we also need to know where things can go wrong once some of our assumptions would be violated.